This is the fifth part of my series on motion in a central force field. In the last lecture, we had taken a look at quadratures which we could solve to find out the equations for orbit or equation for the dynamics. For example, we had this equation which would have given us t as a function of r, which then we could solve to get r as a function of t. Once we have that, we could use that in this equation to get theta as a function of t as well. If we wanted the orbit directly, we would start with d theta dr, or rather dr d theta, which we would get from dr dt divided by d theta dt, and land up with this equation for d theta dr and integrate this, as you can see here. Now we investigated situations where we could actually exactly find out solutions for these integrals in terms of known functions. If you confine yourselves to circular functions, we found that potentials of the form minus a by r plus b by r square or cr square plus d by r square, essentially the Kepler potential and the simple harmonic potential augmented by an inverse r square term, could be solved or rather had quadratures which could be evaluated in terms of circular functions, sines, cosines and things like that. If you extend your list of known functions to go beyond circular functions and go into things called elliptic functions, you find that a larger class of potentials open up for which you can get a solution for these quadrature equations in terms of known functions, in this case elliptic functions, as I said. I just worked out one example of that. U of r is given by a by square root of r plus b over r plus c over the 3 by 2th power of r plus, once again, a term with a 1 by r square. Note that this 1 by r square term is coming recurrently in all of these cases, and we noted in the last lecture that this was not really an accident. So today, let me begin with an explanation as to why this 1 by r square term is cropping up over and over again in solutions that you can actually find out in terms of known functions. It turns out that there is a theorem called Newton's theorem, which essentially says that if you could solve for the motion for a given potential, you could always find from that a solution for this potential plus a 1 by r square term. Let us now try to prove this result. Suppose we have a solution for the orbit, that is r as a function of theta or theta as a function of r, for a given potential u of r. Here I mean that we have a general solution, a solution valid for any energy and any L, angular momentum. So for any arbitrary initial condition. Of course, this solution will obey the differential equation, the quadrature equation that we had actually written down a solution to a while ago, that is dr d theta whole square is given by 2 mu r to the 4 by L square into e minus u of r minus L square over 2 mu r square. This combination is nothing but the effective potential, and the fact that the effective potential already has a 1 by r square term is basically behind the theorem's proof. Let us now consider a new potential, which is not the same as the original potential, but that augmented by a 1 by r square term, u of r plus a by r square. Now, if we look for an orbit equation for this, let's call the orbit equation r tilde theta, just to distinguish between this one, which is r theta, which gives you a solution for the orbit. For this potential, r tilde theta gives us a solution for the orbit in this new potential. Now, r tilde theta must obey a differential equation which essentially is exactly the same as this equation. 2 mu r tilde to the 4 by L square E minus 2 mu r tilde to the 4 by L square U of r tilde. But the new thing is there in this term, which was nothing but simply r square after you multiply this out. In the original equation, the change in the potential has added an additional piece, so that now you have 1 plus 2 mu a over L square times r tilde square. So for the two different potentials, you have slightly different equations, but very slightly different equations. Now, what we will do is change our variable theta to a new variable theta tilde, which is some constant alpha times theta, and plug this into our equation, so that now we are looking for r tilde's derivative with respect to theta tilde, the new angular coordinate that we are going to use. dr tilde d theta tilde's whole square, the counterpart of this thing here, is nothing but dr tilde d theta square times d theta tilde whole square. And that means you have an extra 1 over alpha square here. And that means all of these terms are going to be multiplied by an extra 1 over alpha square. Now it should be quite clear that if we make a choice of alpha in such a way that this factor becomes equal to 1, we are essentially reproducing the same equation that we had for r as a function of theta for the original potential. So if you choose alpha to be square root of 1 plus 2 mu a by L square, this term simply becomes r tilde square. Of course, the constant here and the one in front here also changes, but that can be easily modified by changing L to L tilde, where L tilde is given by L times alpha, that is square root of L square plus 2 mu a. And this gives us an equation which is exactly the same as the equation that we had for dr d theta, except that L has changed to L tilde, and of course r has been changed to this new function r tilde, and theta is now this new coordinate, angular coordinate, theta tilde. And because you have the same equation here as we had for r as a function of theta, we can say that if you have a solution for the original potential, r tilde will be given by essentially the same solution. All you have to do is change the parameter L, which would be there in your solution, to L tilde. And more importantly, change the argument theta to theta tilde. As a result, when you are taking a look at a general form for a potential which can be solved in terms of, say, the elliptic functions, you always have a 1 by r squared term in addition to that. And similarly, if you're looking for a solution in terms of circular functions, it is true that minus 1 by r and r square potentials will give you solutions in terms of circular functions, sines and cosines. However, adding a 1 by r squared term to that will also give you a solution available in terms of circular functions. Once again, let me stress that the only real difference, apart from the change in the parameter L, will be that you have to also consider a different value for the angular coordinate. So, whereas your original functions will come out in terms of, say, cosine theta and sine theta for the original problem, now you will have cosine theta tilde and sine theta tilde in their place. Note that because the relationship between theta and theta tilde involves a factor alpha, which for an arbitrary choice of initial condition, that is, an arbitrary value of L, would typically be an irrational number, even if your original solution happened to be closed orbits, the resulting new solution for the new potential would typically not be closed orbits. This should not come as a surprise because we had earlier talked about Bertrand's theorem. Though we had not completely proven that then, we will give you a more complete proof in this lecture. we had strongly indicated that at least in order to have bound orbit which is closed under arbitrary initial conditions, you must have a power law potential. This part we had already proven. What we had not established completely is that the only possible potentials under which this can happen are minus a by r and cr square. That is something we are going to prove in today's lecture. But let me point out that this obviously shows us that the closed solutions we would get for the Kepler problem and the simple harmonic problem would lead to solutions for similar potentials augmented by a 1 by r square term, but these new solutions would no longer be closed. The difference in the values of theta at which r returns back to the original values were a rational multiple of 2 pi for the Kepler problem and the harmonic oscillator. But for this new problem with this augmentation by 1 by r square, this change in theta will no longer be a rational multiple of 2 pi. The fact that the original problem had closed orbits will not lead to closed orbits for the new potential. Since we are talking a lot about the Kepler and the simple harmonic oscillator problems, let me remind you of the solutions that we had for them. For the orbit equation of the Kepler potential, the integration could be carried out using a simple substitution. I'm not going to go into the details here because we have already discussed this in detail in the previous lecture. And in the end, we ended up with a solution which looked like this. We will talk about the interpretation of this solution in detail in a later part of this lecture. Now, for the 3D harmonic oscillator problem, a very similar series of steps leads to a slightly different final answer, which, once you change over to Cartesian coordinates, gives you the equation of an ellipse. These are the two examples where we have obtained not only explicit solutions in terms of circular functions, but also orbits which are closed for all initial conditions, provided of course they are bound orbits. For the Kepler potential, you get a bound orbit as long as the energy is negative. For the 3D harmonic oscillator potential, which keeps on rising to infinity as you go further and further out, all valid solutions are actually bound orbits. From these examples, it should be clear to you that we have a handle at least for solving the problem of finding the orbit given the law of force. And the standard approach would be to use these integrals, the quadratures that we have written down, and try to evaluate the integrals analytically as we have been able to in these two cases, or numerically, or sometimes using approximation techniques in general. Let me now introduce you to an alternative approach which is usually of more use for solving the inverse problem, which is, given the orbit, figuring out the law of force. It turns out that that particular approach can actually give us a simpler way of solving the Kepler problem, but that is more of a bonus than its real intent. But first, let me just explain to you what this approach is. For this approach, what we do is start with the equations of motion, mu r double dot equals f of r plus L square by mu r cube, and then make a substitution of variables. We call 1 by r u. In the last lecture, we had used u to stand in for r square. Please don't confuse this one with that. This is just a change of variables, and it's conventional to call this variable u. Every standard textbook uses this particular abbreviation, and so will we. At least for the rest of these lectures. U equals 1 by r. Now, we need to rewrite this equation in terms of u, and for that we will need to evaluate r double dot. So we make a start by first evaluating r dot. And it's pretty easy. R is 1 over u. So derivative of r with respect to time is minus 1 over u square u dot. Simply the chain rule for dealing with a function or a function. But notice that you can change the u dot du dt to theta dot d theta dt times du d theta. So this is what you land up with. However, we do have this very important result which we have to keep in mind all the time, that theta dot is actually L over mu r square, or L over mu u square. Plugging that in this expression, we see that the two u squares cancel and you are left with r dot equals minus L over mu, a constant, times du d theta. So this actually bodes rather well for what we are going to do next. The first step has been pretty straightforward. Next step, of course, is to evaluate r double dot. And r double dot is just the derivative of this. So minus L by mu ddt of du d theta, but once again we change that to d theta of du d theta times theta dot, and plugging in this expression for theta dot again, you get minus L square by mu square u square into dtu d theta 2. Now we take this and plug this in our equation. So what you get, mu r double dot becomes minus L square by u square, a single mu in the denominator, one mu cancels, into dtu d theta 2. This is nothing but mu r double dot. The f of r becomes f of 1 over u, and the L square by mu r cube simply becomes L square by mu u cube. But notice that this actually takes a rather simple form if you divide through by u square and the minus L square by mu in front. You get d2u d theta 2 plus the u, if you move this to the other side, is equal to minus mu over L square 1 over u square. That's simply the 1 over u square that comes from dividing through by this u square, times f of 1 over u. So this is the equation which will help us to calculate the force law if you know u as a function of theta. So once you know u as a function of theta, you just plug it in here, calculate the left hand side, and then this will give you f of 1 by u simply by ensuring that whatever is left here times this is a function of u and u alone. So if you are given r of theta, the orbit, hence u of theta, you can evaluate the force law from this. Let us just see an example of that in action. But before that, what we will do is we will express another important equation in terms of this variable u. That equation happens to be the energy conservation equation, which, remember, has already been written down in terms of the effective potential as half mu r dot square plus u effective of r, which happens to be u of r plus L square by 2 mu r square. So now using the result that we have just derived, that L dot is minus L by mu du d theta, we can just rewrite this as half mu L square over mu square du d theta whole square plus u of r plus this term L square by 2 mu r square. But now notice that this is becoming L square by 2 mu u square. This is actually becoming L square by 2 mu du d theta whole square. And u of r in terms of small u becomes capital U of 1 over small u. So the energy conservation equation takes this particular form, L square over 2 mu du d theta whole square plus u square plus capital U of 1 by u. If you did not have this term, this would actually look suspiciously like the energy expression for a harmonic oscillator, except that instead of dx dt you have du d theta, and instead of half k x square you have just u square times L square by 2 mu. This connection between this expression and that for the harmonic oscillator, which is also sort of evident here, this is like the harmonic oscillator equation, except once again the derivative is with respect to theta, an angle, not time. And of course this term sort of tends to spoil that. But if you just look at the left hand side, this is like the equation of motion of a simple harmonic oscillator whose frequency is just given by 1. That is, the coefficient here is just 1. Instead of omega square, which would have been the coefficient for a harmonic oscillator. We will make ample use of this similarity very soon. But before we do that, let's talk about that example of figuring out the force law from the orbit. So, as an example, let's take an orbit of a particle under some law of force, and this orbit happens to be a circle which passes through the origin. Note that this is very different from the kind of circular orbits that we have been talking about for a general situation. This is a circle not centered at the center of motion, not the kind of circular orbit you get at a minimum of an effective potential. This is a motion which passes through the origin, which means Rmin in this case happens to be 0. If you recall the kinds of motion possible that we talked about in terms of the effective potential, this actually implies that you must have a potential which is very, very strongly attractive for small distances. So strongly attractive that the L square by 2 mu r square potential barrier term is overcome by a large negative potential term close to the origin. So we already know that we have an attractive potential which actually falls off very, very rapidly towards minus infinity. So increases rapidly in size, much more rapidly than L square by 2 mu r square grows towards plus infinity as r goes to 0. But we can actually do much better than this kind of qualitative thing. We can just plug the equation of the orbit into our equation that we figured out a while ago and find out the force law from there. Notice the equation for the orbit in this case is very simple. This is your center of motion, so the radius is actually measured from that point. So you need the expression which connects r to this angle theta, and let's take this, the diameter, as the line from which the angle theta is being measured. Then from the fact that the angle in a semicircle is always a right angle, we can easily show that r is nothing but capital D times cosine of the angle theta. So u, the variable that we are going to deal with, is 1 over d sec theta. We need d2u d theta 2 plus u. So du d theta, straightforward differentiation, 1 over d sec theta tan theta. And then you calculate d2u d theta 2 plus u. You get 1 over d sec theta tan theta differentiates to give you sec theta into sec square theta plus sec theta tan theta into tan theta. And of course this is the u. Now, if you combine everything together, what you see is 1 sec theta comes out common out of the whole thing. Then you have a sec square theta and you have a tan square theta plus 1, which again is a sec square theta. So you ultimately end up with 2 by d sec cube theta. So the left hand side works out to be exactly 2 by d times sec cube theta. But what we need is to express this entirely as a function of u. In this case, that's very simple because sec theta is essentially capital D times u. So this expression is simply proportional to u cube. I'm writing proportional to and not bothering to write down the exact formula, which is easy enough to figure out. It's actually twice d squared u cube, simply because we are interested in the way in which the force changes with distance. So, once again, ignoring the constants L square over mu, what we get is minus 1 by u square f of 1 by u is proportional to u cube, which means f of 1 by u is proportional to minus u to the 5. That gives us the force law. F of r, the way the magnitude of the force changes with the distance, is proportional to minus 1 by r to the 5. Of course, recall that we have already said that it has to be very, very strongly attractive at small distances, and that's exactly what this is. Now, we had already mentioned Bertrand's theorem in the last lecture, although we did not completely prove it, but we did mention there that you get closed orbits for arbitrary initial conditions. Only for power law potentials of the form minus k by r and k r square. This particular orbit that we are talking about is definitely a closed orbit. But that is not something we are going to treat as a counterexample to the statement we just made, because the harmonic oscillator potential kr square and the Kepler potential minus k by r are the only ones for which all bound orbits are closed. For a minus 1 by r to the 5 potential, some special orbits are closed. This one actually is a closed orbit. However, most orbits aren't. So the fact that this one orbit is closed doesn't change the fact that the harmonic oscillator and the Kepler potentials are the only ones for which all bound orbits are closed. Talking of the Kepler problem, the differential equation for the orbit that we have figured out just now, d2u d theta 2 plus u, is minus L square over mu f of 1 over u times 1 by u square, happens to provide us with a very simple way of solving the Kepler problem. So let us take a look at that next. In the Kepler problem, f of r is minus k over r square, which as expressed in terms of u becomes minus ku square. Now that has a huge advantage, that the minus mu over L square into 1 by u square in the front ensures that the u square dependence simply cancels out, and you end up with a very, very simple differential equation. d2u d theta 2 plus u equals mu k over L square. The reason why this equation is considered to be so simple is that this is a very well-known and standard equation. Simply the equation of a simple harmonic oscillator. Of course, the term mu k over L square might spoil that a bit, because in a standard harmonic oscillator you should have 0 on the right hand side. But that is also handled very easily. Instead of u, if you use the variable u minus mu k over L square, then that obviously obeys the equation. Second derivative of that with respect to theta plus itself equals 0. After all, mu k over L square being a constant, the u minus mu k over L square has exactly the same derivative and second derivative as this u. So, solving this becomes straightforward because we know what the solution for a harmonic oscillator is. Since this quantity obeys the SHM equation, its solution has to be a cosine theta plus phi, where a and phi are constants which can be fixed only by the initial conditions, and that can be easily rewritten to give you u equals mu k over L square plus a cos theta plus phi. So just by using the fact that we know how to solve the harmonic oscillator equation, we end up with the solution for the orbit, for the Kepler problem, with almost no calculation. Well, no calculation because we already know how the harmonic oscillator equation is solved. Please note that for a general harmonic oscillator equation, you would have an omega square factor here, which happens to be just 1 in this case. So instead of a cos omega theta plus phi, you just have a cos theta plus phi. And now, it is trivial to rewrite this for r. R works out to be 1 over mu k over L square plus a cosine theta plus phi. And just dividing through in the numerator and the denominator by mu k over L square gives us this expression, which can be recast in a form which we have already seen earlier. If you just call this R0 and a times L square over mu k e, you end up with R0 by 1 plus e cosine theta plus phi. So either by directly solving the quadrature equation or by solving our equation for the orbit in terms of u, we have found that the solution to the Kepler potential is given by this expression. In fact, although we have found this solution for an attractive Kepler problem, that is, where you have a minus k in front with a positive k, this solution will be valid irrespective of whether k is positive or negative. So for both the attractive and the repulsive inverse square force law, we are going to end up with a solution which looks like this. Now the question is, exactly what does this solution represent? To see that, let us try to rewrite this after we have chosen the special case, of course, that phi is 0, and thus written this as r equals r0 by 1 plus e cos theta. Let us try to rewrite this in Cartesian coordinates. Now that's pretty easy to do. We see that this expression is nothing but r plus er cos theta equals r0. And if you look at the standard transformation rule between Cartesian and polar coordinates, r cos theta is simply nothing but x. So this is r equals r0 minus ex. Now r is square root of x square plus y square. So the obvious thing to do now is to square this. So what you get is x square plus y square equals r0 minus ex whole square, r0 square plus e square x square minus twice e r0x. And so this is the equation that you ultimately get. This is an equation involving only terms up to order 2 in x and y. And from higher secondary coordinate geometry, we know exactly what kind of a geometrical figure this represents. The answer to that is, this is the equation of a conic section. A conic section, as you all may already be aware of, is simply what you get when you slice a cone. Remember, a cone in mathematics is simply an equation of the form x square plus y square equals some constant into z square. So it's not just a cone which looks like this, not just an ice cream cone. If you think about it as two ice cream cones pasted vertex to vertex, tip to tip, and of course extending to infinity in both directions, then you get what is a mathematical cone. Now a conic section is exactly what the name implies. It's the section that you get when you slice a cone with a plane. Now what kind of shape will you get? That depends on the orientation of the plane with respect to this line, which when you rotate about this axis traces the cone out. So a line like this is typically called the generator of the cone, makes an angle with the axis of the cone. And that, of course, tells us a lot about the shape of the cone. If our plane is exactly normal to the axis of the cone, in other words, in our picture, it slices the cone horizontally, then the section that has been drawn in red here will obviously be just a circle. So that's the case that you have most commonly. And as we will establish, or as you may already know, a circle corresponds to the parameter E in our solution r equals r0 by 1 plus e cos theta, simply being 0. That's sort of straightforward. If E is 0, the equation simply becomes r equals r0. The distance of the point from the center is a constant r0, just a circle whose radius of course is r0. If on the other hand the plane is tilted so that it's no longer perpendicular to the axis of the cone, but not tilted too much, you're going to get something which looks like this, an ellipse. And this corresponds to a value of E between 0 and 1. E happens to be exactly equal to 1 when this slicing plane happens to be parallel to the generator line, any one of the infinitely many generator lines. If that happens, then the curve that is traced out is not a closed curve. It's a curve which goes off to infinity, but just marginally so. And that curve is what we all know as the parabola. This is the e equal to 1 case. When e is more than 1, that is the slice here is tilted more. So it's steeper than the generating line. Then the plane actually cuts the cone into two parts, one on this side, one on the other side. And both of these parts are actually open curves. They go off to infinity on both sides. This is what you call a hyperbola. E is greater than 1. So what we have seen from the equations, this one, which is just a rewrite of the equation r equals r0 over 1 plus e cos theta, is that this is an equation of a conic section, one of these curves. The parameter E is called eccentricity. Now, if you take my word for it, then we can simply skip on to the next step. But you should perhaps ask yourselves a question. What does slicing up a cone by a plane, thus yielding conic sections, have to do with an equation which looks like this? In other words, how are we so sure that the equation of a conic happens to be a quadratic function of x and y? Now, the shape of the orbits for the Kepler potential happens to be of immense importance in physics, especially in celestial mechanics. So let us take a look at the relevant mathematics here in a bit more depth. Now, we may be tempted to say that this equation describes the cone for us, while the plane is described by the equation ax plus by plus cz equals d, where a, b, c and d are constants, a linear equation in the three variables that is. And if you eliminate z between these two, you are obviously going to end up with an equation which looks like ax plus by minus d over c, which is of course our expression for minus z squared is equal to x squared plus y squared, which after you rearrange sides will definitely give you a quadratic involving only x and y. However, that would not quite be the right argument, for the simple reason that this equation that we have written down is actually an equation for the cone only if we take this plane, the plane which passes through the vertex and is normal to the axis, as our xy plane and this as our z-axis. And then the equation that we are going to land up with, the equation that we just mentioned a while ago, this quadratic is really not the equation of the curve which we get when the plane slices the cone. It is the equation of the projection of that curve onto our xy plane, this horizontal plane which I just erased. Of course, that equation is a quadratic. But what we have here is an equation where x and y are obviously coordinates used in the plane of the curve. So in this plane. So we have to give a bit more effort to figure out exactly what that equation is going to be. And that is what we are going to turn to next. Before we do that, I have a rather serious confession to make. I just realized that I have made two errors over the last few minutes, and ideally I should perhaps erase this whole recording and re-record the whole thing. Now I am feeling a bit too lazy to do that, so I am just going to tell you what the errors are. Thankfully, they are not going to matter very much going forward. One of the errors which you may have already noticed is that I have used alpha for this parameter sitting in front of z squared in the equation of the cone, while I have also used the same letter alpha for this angle which the generator of the cone makes with its axis. Not only the generator, if you have any vector which joins the vertex to a point on the cone, which of course would be along one generator of the cone. This is not the only unique generator you have. That will also make an angle of alpha with the axis. Now, this alpha, the angle, and this parameter alpha are of course different. Indeed, if you were at a height of z from the vertex, then the circle that you would get at that fixed height z, essentially the circle you would get by slicing this cone with a plane which is perpendicular to the axis, a circle like this, only maybe at a height z, would have a radius which is given by z times tangent of this alpha. So this alpha here should really be tan square of the angle alpha. So the equation that I write for the cone should look like this. However, what has been important so far is the fact that this alpha is a positive constant. So I did not really make much of a mistake when I just replaced the tan square alpha by just a label. The only mistake was I called it alpha. Now another error, which you must have also noticed, is that when I wrote down this equation, which remember was our equation for the projection of the curve onto our xy plane, I should have multiplied by that alpha there, or actually the tan square alpha there on this side. That again changes nothing of the final conclusion. This equation definitely is a quadratic in x and y. This is the really important part for us. This is not really the equation for the conic section. This is the equation for the projection of the conic section on our horizontal plane, the plane perpendicular to the axis which goes through the vertex. What we need to find is the equation using x and y coordinates which are in the plane slicing the cone and the z-axis perpendicular to that particular plane. So let us now proceed to do that properly. Of course, since we are going to talk about slicing up a cone by a plane, let us first start by fixing the cone. Now, in order to not bias ourselves towards any specific choice of axis to begin with, we are going to make a choice soon, but right now let's keep it perfectly general. We are going to use vectorial notation as much as possible. So the axis of the cone will be given not necessarily by the z-axis or the unit vector k hat, but by some unit vector along it, let's call that n hat. The semi-angle of the cone, basically this angle here, as we have already denoted here, will be called alpha. The vertex of the cone, the point where the two ice cream cones join, is going to be considered to be r0 in our coordinate system. So this is our origin placed in an arbitrary position for the time being. R0 is this vector which joins the origin to the vertex of the cone. N hat is the axis. And if you take any point on the cone, let's say this point whose coordinate vector is r, this vector r minus r0 is a vector which lies entirely along the cone. It's a vector from the vertex of the cone to a point on the cone. Now the point is, every line which joins the vertex of a cone to an arbitrary point on the cone's surface makes an angle alpha with the axis, unit vector n hat. And since the angle is directly related to the dot product, what this tells us is if you take the dot product of n hat with this vector r minus r0, which remember is the vector which is on the cone, you get nothing but the length of r minus r0, modulus of that, into cosine of the angle between them. Now the angle between them, we have been saying that that could be alpha, but of course your point could be on this side, in which case the angle between them would not really be alpha, it would be pi minus alpha. So it's either cosine alpha or cosine of pi minus alpha, which is where the plus minus sign comes from. So the plus sign comes when you're on this side and minus when you're in the opposite side to the axis which you have taken. Of course, the axis of the cone really is not given by a vector, it's given by an infinite line. And both directions n hat and minus n hat are equivalent. But once you have made a choice for n hat, this is the equation you get. Plus sign for points lying on the half of the cone which is towards the chosen n hat, and minus sign for the half which lies in the opposite direction. Now, this was for a perfectly arbitrary choice of origin and coordinate vectors. Now let's make a choice of the origin, which will make our life simpler. Instead of choosing the origin anywhere, let us choose it to be somewhere on the axis. So R0 equals rho 0 n hat. For the time being, we have assumed that the origin will be somewhere in the lower side, so that rho 0 works out to be a positive number. And of course, this rho 0 is nothing but n hat dot product with R0. We are going to need this equation soon. So now we have chosen a special origin. You might ask why we did not choose the origin to be at the vertex. That would of course have made our equation a lot simpler. It would have simply been n hat dot r equals plus minus r small r times cosine alpha. A much simpler equation than what we have at this stage. However, we would essentially want to finally choose our axis in such a way that the slice that we have cut off using a plane happens to be in the xy plane. That is, we will take the xy plane along the slicing plane. Of course, when you do that, you cannot choose your origin away from the plane. The origin would have to be somewhere on the xy plane, and we will have to stick the z-axis to that. Now, since our plane may not and usually will not go through the vertex, if it did, you would just get a point at the slice. Our plane would typically go somewhere below or above. We have no way of choosing the vertex to be on the origin if we want to keep the xy plane as a plane for the final figure. So we have chosen the origin to be the simplest thing that we can do. Is despite that, the plane will be intersected by this vector somewhere, the axis line somewhere, and that point is what we are going to choose as the origin. That's exactly what we have done here. So with that choice, with the origin chosen here, this equation simplifies a bit. N dot r vector minus r0 vector becomes n dot r minus n dot r0, and n dot r0 is of course rho 0, this distance. On the other side, you have mod of r minus r0, and since r0 is given by this, the length of the vector is simply given by the length of the vector r squared plus length of r0 squared, which is rho 0 squared, minus twice r0 into r dot n hat. This follows simply from r minus r0 modulus squared is r squared plus r0 squared minus twice r0 dot r. Of course, there's an overall cos alpha factor with a plus minus sign as before. Until now, we have just chosen the origin as a point where our axis, the axis of the cone, cuts the slicing plane. We will now make a choice of coordinate system with, of course, this point as the origin, and essentially choose our x and y axis in such a way that the xy plane happens to be the plane slicing the cone. So on the plane slicing the cone, our z coordinate will be 0. Now I have drawn the plane as a horizontal plane now, simply because we are used to thinking of the xy plane when we think of a three-dimensional figure as a horizontal plane. Although that's just prejudice, it doesn't have to be. Once you draw it like this, of course, the cone itself gets tilted, and the direction in which the cone gets tilted is simply given by n vector in terms of our x and y coordinates, along with the z coordinate, which is fixed, of course, as normal to the plane which is slicing the thing. Of course, at this stage, only the xy plane has been fixed, which fixes the z direction, but does not fix the x-axis or the y-axis. What we will do is, just to make our life a bit easier as far as the maths is concerned, we will choose the x-axis in such a way that n hat lies in the xz plane. Or if you want it the other way around, you take your n hat vector, which already has a component perpendicular to our plane, something which is fixed the moment the plane is fixed, and a component in parallel to the plane. What we will do is we will simply choose the direction of that component parallel to the plane to be the x-axis. Of course, that makes ny 0, so that n hat dot r simply becomes nxx plus nzz. This is simply the equation we wrote down a while ago. This is just the square of both sides of that equation. After you take the cosine alpha from this side and push it to the other side. In addition to this, which is the equation of the cone, you have to satisfy the equation of the plane, which simply happens to be z equal to 0 in our coordinate system. And because of our special choice of the x-axis, n dot r for any point happens to be nxx plus nzz, and for the points that we are looking at, where z is 0, n dot r happens to be just nxx. So in this whole expression, we have everything that we can replace in terms of x and y coordinates. The z, of course, is 0 throughout. This is nxx, so is this. We, of course, have an r square, which is simply x square plus y square. And when you put everything in and move everything to one side, this just takes a bit of algebra. We end up with this equation, 1 minus nx squared sec square alpha x square. That's just writing this as x square plus y square and taking this term away from that, plus y square, which comes, of course, from r square, minus twice r0 nxx times tan square alpha. The tan square alpha is simply a sign of sec square alpha moving to this other side, equals tan square alpha rho 0 square. Now let's just compare this with the equation that we have. We have 1 minus e squared x square plus twice e r0x plus y square equals r0 square. In fact, from this we can immediately read off e as nx sec alpha. And it might seem that it actually tells you immediately that r0 equals tan alpha rho 0, but that actually is not quite correct. Because if you took that, then twice e r0 will definitely never be equal to minus twice r0 nx tan square alpha. To see what is really going on here, let us try to recast these equations into a more standard form, the form of a conic section where the origin is placed at the center. First, let us try with our equation from the slicing up the conic. So when you start with this equation, what you need to do is take into account this term, the linear term in x, combine it with the x squared term by completing a square. Now that's pretty easily done using the formula a plus b whole square is a square plus 2ab plus b square. You can easily see that after you take this factor out, you can write this term and this term together as x minus rho 0 nx tan square alpha by 1 minus nx square sec square alpha's whole square. Y square stays as it is. There is an additional term which comes in because of the square of this term on the left hand side, so you have to add that to the right hand side as well. And when you just simplify the right hand side a bit by taking rho 0 square tan square alpha divided by this common, you get 1 minus nx square sec square alpha from the first term, nx square tan square alpha from the second, and therefore everything boils down to simply rho 0 square tan square alpha by 1 minus nx square sec square alpha. And here you get 1 minus nx square using a standard trigonometric identity. And since we are dealing with n which is in the xz plane entirely, 1 minus nx square is simply equal to nz square. So this is the final form which the right hand side takes. Now the obvious thing to do here to write the equation in the standard form would be to change your coordinates. We would go in for new coordinates x tilde and y tilde, where x tilde is given by simply x minus rho 0 nx times tan square alpha by 1 minus nx square sec square alpha, and y tilde is the same as y. No shift required here. And once you do that, this equation takes the form 1 minus nx square sec square alpha into x tilde square plus y tilde square equals this quantity on the right, which is a standard for a conic section. Now let me point out one thing. We couldn't have done this if nx sec alpha had been exactly equal to 1. Then this step would have been illegitimate. Of course, if nx sec alpha were exactly equal to 1, we would be dealing with an equation which only has a quadratic in y but a linear term in x, which really is an equation of a parabola. That is a sort of intermediate situation between the ellipse and the hyperbola. We are just not considering this special case at the moment. We could take that case into account consistently, but let's just forget about that for the moment. Now let's come to the other equation, the equation that we had already derived from the central force field problem of Kepler. This was the form we had ultimately, and I have deliberately written x prime and y prime here for the coordinates, just because the slicing a cone coordinate system that we had introduced earlier happens to be different from this coordinate system which Kepler's problem had led us to. But now we do the similar thing. We complete the square on the left hand side, again ruling out the case when e equals 1. Since E is nx sec alpha, of course the same situation occurs in both cases. You end up with a parabola there, and hence the quadratic term in x completely drops out. So this is what you get, x prime plus er0 by 1 minus e square whole square. In the other cases, plus y prime square equals r0 square plus the square of this term, of course multiplied by the 1 minus e square on the outside. This is what you get and simplifies to r0 square by 1 minus e square. Once again we carry out a change of coordinates, trying to rewrite this equation again with the conic center at the origin. And in order to do that, we will introduce the same coordinates x tilde, y tilde with respect to our new coordinate system. But x tilde is going to be x prime plus er0 by 1 minus e square. Y tilde is going to be y prime. And once you do that, this is the form the equation takes. Now it becomes very easy to compare the two equations. They are identical equations, provided you identify E with nx sec alpha. That's something we have already done before. And r0 square by 1 minus e square with this expression. And of course, this 1 minus nx square sec square alpha here in the denominator is exactly the same as 1 minus e square. So this gives you a very simple final result that r0 is rho 0 tan alpha nz. Now, as we were saying, the difference in the two equations that we had obtained here really stemmed from the fact that we were using different origins, or equivalently different coordinate systems. Here we had placed the origin at the point where the slicing plane intersects the axis of the cone. Here the origin was placed obviously at the center of the force. The two do not coincide, and what you will end up with here is finally a relationship between the two. If you look at x prime with respect to x prime is of course x tilde minus er0 by 1 minus e square, but x tilde is also x minus this quantity. Here I have just written er0 by 1 minus e square in terms of rho 0, nx, ny, nz and so on. And after that, this is the final expression we get. So this tells us that if you want to find out the position of the center of force, which as it turns out from the equation is the focus of the conic section, you have to move away along the plane from the point where the plane intersects the axis through a distance given by this. The expression may look complicated, but ultimately is simply a statement that the center of the force or the focus of the conic section is not really at the point where the axis cuts our slicing plane. We have a lot more to say about the Kepler problem, especially about the nature of the orbits, conditions under which different kinds of orbits are produced, as well as physical consequences of the kind of orbits that you get in this particular potential, which of course is what you see in gravitational interaction as well as in Coulombic interaction. In the next lecture, we will first talk about an alternative way of defining a conic and see how our formula r equals r0 over 1 plus e cosine theta corresponds to that directly. We will also have a lot more to say about this particular equation and try to describe various kinds of orbits and their properties based on this. There will be many other topics to talk about, and we will perhaps be talking about this topic for a couple of lectures more. But till then, goodbye.